So I'm an architect, and we build things, usually small things. But on the side, we also like to speculate and sort of imagine, and that's what I want to show today, some of our speculative kind of fictive work. We're based in New York City, and until recently, New York was home to the tallest buildings in the world. There's still a lot of tall buildings in New York. Most recently, this one here was completed, which is 432 Park Avenue. It's the tallest residential building in the world. It's a self-contained building. The upper floors are reserved for the extremely wealthy, and the lower floors are smaller units for their housekeepers and service staff. So people living in that building don't really have to leave the building. It's essentially a self-contained world. And so this interest in height led to kind of an analysis of buildings going back to prehistory. So on the left side, we have caves and teepees. So there's a little teepee and like a yurt. So that's where we came from. Let's say 4,000 years ago, roughly. We started building. Sorry. So then we started making taller structures out of stone, which are pyramids, which were funerary structures, and then reliquary structures like stupas, cathedrals, monuments, and then business structures. And with each generation, they got taller and taller, until now we have the tallest building in the world, the kind of Burj Khalifa, which is a mixed-use residential hotel business structure. On the top, you see like a line graph showing the same thing, basically height of buildings through time. And the right side of the graph is the proposed buildings up through 2050. That's going to be a 2 kilometer or 2.4 kilometer tall building, also proposed for Dubai. But also on this chart is the aerial kind of age, the space age, and that's what we're actually interested in, is us leaving the ground, right? So architecture is necessarily grounded, but with hot air balloons and powered flight and the space age, we're starting to leave the ground. And since 1989, there have been people permanently living in space 400 kilometers above the ground in laboratories called Skylab or Mir or ISS. So our general thesis in the work I'm going to show you is looking at how can we think about architecture in the air. Because our world is essentially composed of 3 spheres. We have the lithosphere, which is the ground that we stand on, the stone, the hydrosphere, which is the oceans, and then the atmosphere, which is where we live. And so fish, aquatic life, they tend to inhabit the hydrosphere in 3 dimensions, like from top to bottom, they fully inhabit the hydrosphere. But we're essentially stuck at the bottom of the atmosphere. We're like bottom dwellers. And so we want to really kind of get into this space here. We think that could be maybe the future of architecture. So just some general basics about the atmosphere. It's a layered structure, and most of what we know of the atmosphere happens here. This is where all the weather is, and hot air balloons and commercial airplanes travel at that height, which is where the jet stream is, about 30,000 feet or 10 to 11 kilometers above the ground. And most of the clouds happen here. Once you get above this troposphere, it gets pretty extreme. There's a lot of radiation. The temperature drops and the pressure drops. So this blue line is essentially the pressure. It goes to a vacuum pretty quickly. And the red line is the temperature. So as you go up higher, the temperature drops. There's a weird inversion here where it gets warmer, then it gets cold, and then it gets really hot again when you go super high. So the projects I'm going to show sort of start close to the surface, and they go all the way up to pretty far out. So when we started thinking about this, and this is the work we're going to show is over a couple of years, but we're thinking about how we can actually support building-like structures in the atmosphere without using motors or propellers or powered support. So there's three categories that we kind of broke the suspension systems into. Aerostats are essentially like a balloon, like a hot air balloon, which is like a bubble in water. It's lighter than the surrounding medium. So if you think about the atmosphere as a fluid, the balloon is like a bubble in the fluid. Aerodynes, essentially airplanes are aerodynes, also kites or gliders. And then the third category would be the orbital, which consists of satellites, space stations, or the space elevator, which is an interesting idea as well. So looking at precedents for each of the categories, aerostats go back to the late 1700s in Paris. Was the first hot air balloon. And there are some wild ideas that people had at the kind of birth of balloons. This is showing like the battle of balloons, like the British and the French using cannons to fight each other. This balloon can support 60 people. And it has like little architectural structures on it, which I thought was interesting. And then the British were also very afraid of the French invading with these kind of giant army balloons. What's interesting about this image is that the hot air is actually ground-based, like it's separated from the balloon, so the flame is just basically a campfire, and then the balloon goes up. So I guess when the wind blows, you kind of lose your lift. And then they even were thinking about them as boats. So this lady here, she's oaring through the air, like so it's literally like the air is a heavy fluid. And the North Pole was explored by balloon. It wasn't successful. They crashed. And yeah, it was pretty tragic. And then the Empire State Building, which was the tallest building in New York for a very long time, the top of which was designed as a dirigible station. So the idea was that the city would become, the transportation system in the city would be through dirigibles, through balloons. So this was supposed to be the first station. This image is actually a fake. That actually never happened. There was an attempt, which this is a real photograph of the Empire State Building. They docked for about 3 minutes and were able to transfer some newspapers. But because of the high winds and stuff, it was kind of a dicey operation. So we took this idea and applied it for like a competition. Post-Katrina, there's a huge hurricane in Katrina that displaced a lot of people, caused a lot of damage. So New York City got alarmed by that, and they asked architects to come up with ideas for temporary housing post like a Category 4 hurricane that might hit New York. So one of the problems with Katrina was that half the population was displaced, and they left New Orleans and they didn't come back for a long time. And even now, it's only about 80% of the people came back. So this idea is literally just keeping people rooted to their house, so that if your neighborhood gets destroyed and the house is unlivable, there would be these temporary inflatable housing units that would literally connect to your old house. So utilities would get extended up, the plumbing and electricity, and you can sort of turn a wheel and lower it to get down and go to work, and then you can come back home, etc. So these are just some schematic drawings of the balloon structure. You have two helium pockets for redundancy, and that's a deployment sequence where, just a truck-based pallet that will get inflated and then lifted above the houses. So it's rapidly deployed. And the idea is just to keep people within a community and involved in the rebuilding process of their neighborhoods. The city was interested in it, but what we found out is actually that helium is now considered a precious resource. There's only so much of it in the world, and we can't make any more of it. So we started looking at other ways of supporting structures. So now we go to the aerodyne category, kites in particular. This is maybe one of the first examples of a man-lifting kite. It was a Japanese, I don't know, he was some kind of criminal, and he was exiled to an island, and he escaped from the island with this giant kite. Kites used as propellant or drives for boats, so this is like a boat driving kite, man-lifting kind of flying kites, and then these multicellular giant kites, which I don't know if you can see, but there's a woman inside of it, and which led to gliders and the Wright brothers developing the powered flight. So this project looks at a community of different kind of building types supported by kites way up in the atmosphere. There's a thing called a jet stream, which basically is about 10 to 12 kilometers in the air, and the jet stream is a constant west to east flow of air at 160 kilometers an hour. It doesn't vary much in terms of the strength of the wind, so you can basically depend on getting support and lift from it. It does move, though, geographically. It kind of shifts its location with respect to the ground, and it's actually responsible for the weather we have. So these are maps of how the jet stream might change from day to day or season to season, and these little lines are the kind of kite structures. So it's looking at borderless communities, like communities that are transnational or not even national, I guess. Communities that don't have to pay taxes because they're not grounded, so there's no property tax. And we started looking at each unit as kind of having to survive in the air without the ground. So it has to have some soil on its roof to be able to grow things, a funnel-like shape in the middle that can collect water, and this kind of expandable water bag that can collect water for drinking and etc. So the third category, and this is where our most recent projects are, is the orbital. So we all know how satellites work. Generally, there's a lot of them now. That's an image of all the satellites. And there's also, I guess, a lesser known idea that's been around since the 1950s called the space elevator. And what it is if you extend a cable from the Earth's equator to a certain height, it's tens of thousands of kilometers, the cable would essentially stay upright because of the Earth's rotation, and the center of mass would be about where the geosynchronous orbit or geostationary orbit is. So the idea is that once the cable is taut, you can use it as basically an elevator to lift material into space. So it's a much more efficient way of transporting goods into space. You don't have to burn propellant. So we took this idea and kind of hacked it in different ways. This is actually the space station. So there's people up there now living up there. So what we did is we came up with the idea for the tallest building in the world. It's about 32 kilometers tall, and NASA has a mission plan for 2021. It's called the ARM mission. It's the Asteroid Redirect mission, and they're planning to go out into space, grab an asteroid, or part of an asteroid, and redirect it to lunar orbit. So if we can do that, we can also take an asteroid and put it into Earth orbit. And if we can get a large enough one, we can imagine that we can drop a cable down from that asteroid. And from that cable, we can actually suspend a structure, like a building. And if we put it into a geosynchronous orbit, its ground trace would be essentially like a figure eight, with a crossing line at the equator. So over 24 hours, it would essentially travel in a figure eight. And yeah, so that's the support for the building. It's a giant asteroid with cables. I don't know if you can see the cables, but there's cables coming down. And so this building, this is the ground here, and the building is this line here, and that's 32 kilometers high. What we found out, when we look at extreme height, is that there's some curious things that happen. The daylight is actually 40 minutes longer at this height. So if you're down here at the ground and you see the sunset, you can take an elevator up and you can see the sunset again. So you can actually see two sunsets in this building. The shape of the windows changes because of the pressure, because it's a near vacuum at the top of the building. And this chart is sort of showing the use over time. So like if that's midnight, that's 12 noon, 1 o'clock, 2 o'clock, etc. How people can move within the building, like the various heights of the building. So like during working hours, they would be close to the surface, and they can actually even transfer between the moving tower and the surface. So these are just some images of inside the tower. So the lower parts would be business-centered, like office spaces, or greenhouses, green spaces. And the residential parts would be kind of midway up, and then the upper reaches where it's kind of dark and spacey would be more like a worship-like or funerary-type spaces. And then, of course, because the tower is moving, like how do you get on and off? So we looked at like a linkage system that would provide a certain amount of contact between the ground to allow transfer of people and goods. You can also, I guess, take the short way down with parachutes. And then just what the tower might look like as it's passing over Midtown Manhattan. And then expanding the idea, like, so if you can do a single tower, you can extend it into a city. So we can actually suspend an entire city. And we looked at, taking the world's population at a certain density. Like if you had 7 billion people and you gave them 50 square meters per person, how big would that city need to be? And it's actually not that big. So this is the idea of expanding the system, so you can just wrap around the entire planet to make a giant equatorial ring city. And then we looked at all the cities around the world and how can we translate them or relocate them to a single line. So we did a couple of different versions of this, but just kind of understanding basically that neighboring countries tend not to like each other. We tried to make sure that neighboring countries were in different parts of the line. So there's just some images of the suspended city. This is still kind of a work in progress. It's not really reached a level where it's showable, but we're just kind of previewing it. This is kind of the end of it where it's still under construction. The other interesting thing about, so it can only exist on the equator. And the equator is an interesting place. It has equal day, equal night. The temperature is very comfortable. So at the height of the city, you wouldn't need air conditioning, you wouldn't need heating. It's constantly at 68 to 70 degrees, or about 16 degrees Celsius. And the sun would set along the length of the city. So east and west is like in line with the city. So there's some kind of curious things with the equator. I think I'm over time, so I'm just going to breeze through this one. This is just conceptually imagining like if you were to build a tower and then you just kept going and going to make it super tall, like 50,000 kilometers tall. At some point, the mass of the tower would be equal to or greater than the mass of the Earth, like conceptually. At which point it would essentially break off and take off, like it would actually launch itself into space because it would have reached escape velocity, which we did the calculation for, and it would sort of spin through space. And as it's spinning, it would start to create its own gravity, right? So in the middle of the pivot point, you have 0g, and then as you move along the length of the tower, you get greater amounts of gravity, so you get like a spectrum of gravity along the length of the tower. And then the tower could actually end up in reaching a different planet. For example, it could show up at Mars and go into orbit around Mars. Just some views out from the tower as it's traveling through space. And the tower in space. I'm going to skip this one. It's looking at comets as interstellar vehicles. And so we've been traveling further and further up into space, and now we're landing again on Mars. So this is a project called Mars Icehouse. It's a competition that we entered and funded by NASA. It's autonomously deployed via rocket with robots that essentially excavate water, and then 3D printers that print the structure. It's a habitat for astronauts, and basically an exploration mission on Mars that would last a year. So it's a habitat for astronauts. It's not colonization. It's just purely for exploration. And ice water is used primarily because it's great for radiation, like it shields against cosmic radiation. Also, we wanted to allow natural light to come in because the psychological factor of getting to Mars is intense. That's it. Yeah, stop.